Hi, my name is Onasci, and for the fall 2018 semester, I would like to be a peer mentor for Chemistry 102, which I took last semester with Dr. Tiani. The reason I would like to be a mentor for Chemistry 102 is because I loved solving every single problem, and it was more like solving a puzzle as opposed to doing homework that I was just required to do, and I would love to help other students enjoy it as much as I did. Also, I loved Chemistry 102 because it explained everyday concepts that we just do, like putting salt in water when boiling it, and why we have to cook cake mixes at a different temperature in high altitudes. It explained these everyday concepts to us that we really don't think about in everyday life as we're doing them. So today for my problem, I will do an acid-base titration of 35 milliliters of 0.15 molarity acetic acid, a weak acid with a Ka value of 1.8 times 10 to the negative 5, with 0.15 molarity sodium hydroxide. It's a 4-step problem, and in each one I will be solving for the pH. So first we have 0 milliliters of our base added, but at this point, since we have a weak acid, it will dissociate and form hydronium ions, which we need to find the pH. So we have 0.15 molarity in the beginning, initially, and then we're going to minus an amount that we don't really know, so we name it X, so minus X. And then over here we get our conjugate base and our hydronium ion, which we get as plus X and plus X. So at the equilibrium we have 0.15 minus X, X, X. Now our Ka is an equilibrium constant so it's going to be using the equilibrium amounts here. So X squared on top over 0.15 minus X at the bottom. We can neglect this minus X. So when we solve for X, we are basically solving this. And we get this amount, 0.00164, as a X, which happens to be our hydronium ion concentration. We just use the regular pH formula and put this amount into the negative log of 0.00164 equals the pH, which is 2.78 for this step. For number 2, we are adding 17.5 milliliters of our base, of our strong base. At this point, we're halfway to the equilibrium point. And if we're halfway to the equilibrium point, our base and our acid and our conjugate base that we form over here are going to be the same amount. So that's going to make, we're going to use the Henderson-Hasselbalch equation of pH equals pKa plus log of conjugate base over acid. However, since these amounts are equal, this ends up being 1, so we just neglect that, and then pH equals pKa. So pH is going to equal negative log of the pKa of acetic acid, 1.8 times 10 to the negative 5 equals 4.74. Third step, we're adding 34.5 milliliters of base. Now we are almost to the equilibrium point, but not quite. So we're going to have to figure out how many moles and how many moles of our conjugate base and how many moles of our acid are present in solution. So I like to use millimoles because it's smaller numbers and it helps me keep track easier, and it's easier to use since we have milliliters anyway. So in the beginning we have 5.25 millimoles of our weak acid, which I just write as HA so I don't have to write all of that. And then in the beginning we find we're using 34.5 and 0.15 molarity. We have 5.175 millimoles of our base. Water is just neglected, and then we have 0 millimoles of our conjugate base. Now we use all this base, we're going to minus it from 5.175, and then we're also going to minus this from our acid, our acetic acid. So at equilibrium we have 0.075 millimoles of acetic acid, 0 moles of NaOH, and we have gained 5.175 millimoles of our conjugate base. So right here we use the Henderson-Hasselbalch equation again, using pH equals the negative log of 1.8 times 10 to the negative 5, our pKa, and plus the log of our conjugate base, 5.175, over our acid, our acetic acid, 0.075 millimoles. This, according to the equation, this shows it as molarity, but because it's just a ratio, we can use the millimoles instead. We don't have to get the molarity. So I have used the millimoles over here, and when plugging all this in the calculator, we end up getting pH equals 6.58. Our last step, question number 4, is 35 milliliters of base. So at this point, all of our acetic acid has been formed into its conjugate base. And we're going to have to use the conjugate base, which also dissociates. And we're going to have to use basically something like we did over here. But instead, we have our conjugate base, so 0.07, and the reason that we have 0.075 is because since all of our acetic acid has formed into its conjugate base, we have 5.25 millimoles of the conjugate base over 70 total milliliters, because 35 milliliters and then 35 milliliters over here. So that ends up being 0.075 molarity of our conjugate base. So we have 0.075 molarity of our conjugate base. Somehow we lose some amount, so we do minus x, and we get this plus x of hydroxide ions plus x of the acetic acid. So 0.075 minus x, x, x. Then we can use the Kb, which is just like the Ka, except the Kb we can do the water dissociation constant divided by the Ka in order to get the Kb, 5.56 times 10 to the negative 10. Then we use the Kb over here, and similarly to step 1 of our problem, I just set up an equilibrium constant equation, neglecting that minus x, and then once we solve for x, we actually happen to get the hydroxide ion concentration in this. And we can use that to find a pH, but we must do POH equals negative log of this, which gets us the POH, and then pH is just going to equal 14 minus 5.19, our POH that we have gotten before, and we get 8.81, which happens to be a basic solution, which makes sense at this point since we have the conjugate base present in solution.